All right. Howdy. Good morning. Thank y'all for being here. Happy Thursday. Hope y'all are all doing well. Um, today, question? Uh, Tuesday. Wow. Yeah, it is. Thank you. Exam is on Thursday. Um, the scores from exam one were entered last night, and the grades from quizzes three, four, and five were entered last night. I'm gonna talk about the exam and pass those back at the end. Um, Today's the last lecture before we take exam two. So I wanted to make sure that I covered everything that I wanted to talk about, both for homework six as well as for exam two. And then I'll pass back the quizzes and the exams at the end. So let's move forward. This is just reminding you about the exam um, Thursday in class, full class time. Um, the review is on the Google Drive. If you haven't taken a look at that, that's probably a good thing to take a look at so that you know, just so that you're making sure that you're aware of what the scope of the exam two is. Basically, that's lectures 7 through 12, homeworks 4, 5, and 6, and then it corresponds to like the end of chapter 4 in Speckhoff notes through chapter 7. I also, question? Yeah, so after I pass back the quizzes, I will go ahead and I'll post the keys too. Um, so yeah, the formula sheet is on the Google Drive too. So like if you are looking in our class drive, under exam materials or review materials, let's pull it up real quick. I don't know why it keeps wanting me to open that. Exam materials and exam two formula sheet. So that is the formula sheet that's going to be attached at the end of your exam. Um, it contains basically all the same formulas from exam one, plus an extra page that represents the new equations and models that we've learned in exam two, and then some other tables and graphs. So make sure you're familiar with that, right? You don't want to go into the exam not knowing what's on the formula sheet. Make sure that you are practicing and that you are thinking about and understanding the differences between the different models. One of the like mistakes that I saw on exam one, I don't know what happened to my screen, sorry. Um, one of the mistakes that I saw in exam one was people were mixing up models, like mixing up multi-region and multi-group, and things like that. So for the different models, make sure you're familiar with kind of what they represent and what kind of scenarios they tell us about, so that we're not not getting points taken off when we're answering questions because we're mixing up like one model from another. Okay, there you go. Sorry about that. So yeah, first page is the same as the last one. Second page is the new stuff. And I guess another thing to note is that there will be some formulas that you might need that are not necessarily on here. So don't assume that this contains every single formula you would possibly need. There are some fundamental formulas that you're not going to find on here, and so yeah, just that's part of knowing the formula sheet, is so that you know what you have, and then you also will then know like, okay, this is what I have, and these are the things that I like would need to possibly remember based on the kinds of equations that you were seeing on the homeworks, or the kinds of equations that you yeah, mostly based on what you were seeing in the homeworks. So if you weren't aware of that, that's there. I would use that as I was studying and preparing for exam two. Um, and so yeah, exam two is going to be really similar to exam one. Hopefully, when you get exam one back, you will see that it was similar to what you would have seen on like the first couple of homeworks. So yeah. Um, and I'll talk, like I said, I'm going to pass back the exams at the end of class, and we'll talk more about that at the end. So main models that we've kind of introduced in the kind of second exam material, in terms of all the time-dependent stuff, is the point reactor kinetics equations. These are our equations that we developed that will tell us about the time dependence of properties of our reactor. So that in total function, that the way that we derived these equations, that represented the neutron density. But in the homework, when you redid the derivation, you should have seen that that n of t actually just represents any amplitude function. So it could be a lot of different things depending on, you will see these equations written where n total is replaced with, maybe it's replaced with the power density, or very common, it's just replaced with the reactor power. So you'll see the n total variable replaced with other integral properties of the reactor, which is an okay thing to do with these equations. And either way, it's going to tell you, these equations tell you about the time dependence of those variables, especially when we have some kind of reactivity insertion or removal from our system. If the system's reactivity changes, these are the equations that'll tell us the time dependence of those variables in our reactor as a result of that change. We talked about different kinds of things that could be causing our reactivity to change. We want to, in general, be aware of all of these different factors. When you're using the point reactor kinetics equations, they just tell you, they'll tell you something has happened to the system which will make its reactivity change. And these are some of the things that could happen to make that happen. The to get equations, so we were just saying that the n total and like the ci, those are the solutions to the n-hour equation. They look like a sum of exponentials, and these exponentials have time constants. And so to find the solution, we have to find the time constants. And the way that we find the time constants is through the n-hour equation. The n-hour equation is the equation that we can solve to get these time constants. And whenever you solve the n-hour equation, there are just as many time constants as there are exponential solutions in your functions. In the functional form for each solution, it's a series, it's a sum of exponentials. There's I plus one exponentials corresponding to the number of equations that we're starting with. The point reactor kinetics equations, there's one equation for the neutron density, and then there's I equations for the precursor density. So in total, these give us a system. Um, these give us a system of I plus one equations. Each solution in total and Ci of t will be a sum of exponentials, and there are I plus one exponentials, and there are I plus one time constants that we can solve for using the n-hour equation. And then the solution looks like a bunch of exponentials. Those time constants are in the exponentials, and they can be positive or negative, and the form of those time constants is going to affect how my solution grows with time. Does it increase exponentially? Does it decrease exponentially? Or does it remain constant or steady if one of our time constants might be 0? And so we talked about graphically solving the n-hour equation. This is a good graph to be familiar with to understand the similarities and how these time constants relate to the value of my reactivity insertion. So when you look at the n-hour equation, the left-hand side is the reactivity insertion. And on this graph, that's plotted as just two horizontal lines, depending on if the reactivity insertion was positive or if that reactivity insertion was negative. And then the right-hand side of the n-hour equation is this function of omega. Notice that all of these terms here, it's just functions of omega, because big lambda is just a constant, bi is just a constant, and lambda I is just a constant. So you would know those constants, and then you could plot the right-hand side of this function as like a function of x, which in this case, the input variable x is representing omega, which is the time constant. And so what this equation is telling us, like the solutions to this equation are where the reactivity insertion lines intersect with the n-hour equation. And there's going to be I plus one intersection points, and each of those intersection points has a corresponding like x value or omega value that represents the time constant for so basically each time constant has a each intersection point has a corresponding time constant. And if the reactivity insertion is positive, notice that the first I of these time constants are all negative, and then there's one time constant that's positive. It's the same. There's one time constant that has the same sign as the reactivity insertion. If the reactivity insertion is negative, then we have the the first I are still negative, and then also the other time constant omega zero becomes -2, and this omega zero is like the algebraically largest time constant, or it's like the one that's always going to be kind of closest to zero. Um, so if the insertion is negative, all of my time constants are negative, and one of them, omega zero, is like the least negative. And then if the reactivity insertion was zero, then all of these I time constants would be negative, and then one time constant would be zero. So in general, there's like an interpretation of this graph that we want to be familiar with, which is what's being shown on this slide. And that's basically I of them are always going to be negative. One of them is going to match the sign of the reactivity insertion. And if that reactivity insertion is negative, then omega zero is bounded by lambda one, which is the minimum lambda value in our the minimum value for our delayed neutron precursor groups. So notice how if this horizontal line goes down, then the value of this time constant omega zero is going to get closer and closer and closer to this horizontal asymptote, which corresponds to negative lambda one. So that's why we're saying that lambda zero is bounded by negative lambda one. And that lambda one has a corresponds to the precursors that have the longest half-life that we consider in our groups. So one of the things to kind of be familiar with is that there's a lot of delayed neutron precursors. Some of them have very, very, very long half-lives. Some of them have very, very short half-lives. We kind of only consider a range of these precursors that's important to the time dynamics in what the point reactor kinetics and in our equation can tell us about. So the precursor that is the longest half-life corresponds to mostly 87 bromine in in uranium fuel. And it has a half-life of 55 seconds. So if you know its half-life, you can figure out what the corresponding lambda minimum is, which is 1/80. And then we talked about the reactor period, which is the inverse of that time constant. And so the reactor shutdown period is the inverse of that minimum time constant, which corresponds to 80 seconds. So basically what that tells us is that if the reactivity insertion in our system is negative, this 80 seconds is like the fastest that our reactor could possibly shut down. And in reality, it's probably going to take longer than 80 seconds, but the reactor shutdown period would be a characteristic time of 80 seconds. Um, and so we then talked about the different kinds of, if we have some change to our system, how does the system behave as a function of time? Um, does it increase exponentially? Does it decrease exponentially? Does it grow linearly? Does it grow in a steady state? And that just depends on basically two things: if I have a source in my reactor or if I don't, and also if my reactor, what's the criticality state? Is it critical or supercritical or subcritical? So we want to know these different kinds of cases because I could ask you about any of them, and then I could say, in this case, draw me a graph that shows how the behavior of my power or my neutron density or any integral property changes with time. So if you know these cases, then you can identify which case you have, and then you can draw the right graph. So when we talk about the point kinetics equations, they don't factor in feedback effects. And the feedback is a phenomena that's going to happen because, like, if we make some change to our system, like suppose we remove all the control rods from our reactor so that the power of our reactor starts going up, that means that the temperature of our reactor is going to start going up. And like at a certain point, that can't go on forever. There are going to be, as a result of those temperature changes, it's going to change other things in our system, which are going to make the system's properties not continue in the way that they were before. So like if that population is increasing exponentially, it can't increase exponentially forever. There's going to be feedback effects that are going to result in the power and ultimately the temperature decreasing at some point. So there are a lot of factors in our reactor that cause feedback, but a lot of them are caused by temperature changes. And so just in terms of temperature, like if we want to remember that every fission has like about how much energy released per fission? Mhm. 200 MeV, and our fission reaction rates in our reactor are on the order of like 10 to the 10 or 10 to the 12. So if you have 10 to the 12 like fissions per second, each fission is producing 200 MeV per fission, then there's a tremendous amount of heat being formed in our reactor, and that is going to affect our temperature. Um, and there's a lot of other things that are impacted by temperature. Our cross sections depend on temperature. Um, our uh, our reactor properties depend on temperature, like densities and things like that can vary as a function of temperature because of things like expansion. And so um, in that thing I was just illustrating where our fuel heats up because we've removed all of the control rods from our reactor, what's going to happen is that as our temperature heats up, our cross sections in our fuel are going to start to broaden, especially in the resonance region, and that's going to result in basically more absorption in our fuel that doesn't result in a fission. And so ultimately, like when you increase temperature and those resonances broaden, it actually reduces the reactivity of our system. So that's an example of negative feedback where a temperature increase ultimately results in a reactivity decrease because of how the temperature affects other things in our system. We like when our reactors have negative feedback because it makes them controllable. If they had positive feedback, then an increase in temperature would cause an increase in reactivity, which would cause a further increase in temperature, further increase in reactivity, and then the reactor blows up. We want it to be such that if the temperature goes up, there's mechanisms to make the reactivity go down so that we don't have some kind of like runaway chain reaction type of situation. Um, so there's positive and negative feedback, which is what I was just talking about. This is like a feedback loop diagram that's kind of illustrating how some reactivity change could affect the power, which could cause a change in the power, which could cause a change in the temperature, which could cause a change in our cross sections, which could ultimately cause a change in our reactivity. And for most fuel, that change in our cross sections is going to result such that the reactivity goes down if this temperature goes up and the initial reactivity goes up. And as a result of all of these things giving us a negative change in reactivity, that negative change in reactivity is going to propagate back into our system, and there's a feedback effect. So we want negative feedback, and we have some ways to kind of characterize how different parameters in our reactor will affect our reactivity, and those are called coefficients of reactivity. So in general, a reactivity coefficient is going to be defined by, so we use a symbol alpha for a reactivity coefficient. And fundamentally, what alpha describes is how your reactivity changes as a result of some change in some property of my reactor. So X could be a lot of different properties of our reactor. We talk about temperature a lot. It could be pressure, it could be the void fraction. And so we have reactivity coefficients for these different variables, which describes how the reactivity of our system changes when those variables change. Um, so in general, this is how we could write it for any general quantity X, and then we could write this for various different quantities depending on what the quantity was. And in general, if it's a change in reactivity over some change in X, in other words, if it's like a derivative, what's the way that I can simplify the derivative? Like if I didn't know what the actual function was, what's the way that I could simplify a derivative? Billy? Oh, so not necessarily if you so when you talk about the definition of a derivative, it's the limit of some like change in y over some change in x as we make the change in x, as we take the limit as that change in x gets very, very small. But if we wanted to just approximate this derivative in like a more simple way, yeah, Yeah, we would just approximate because the derivative fundamentally is just a slope, but it's like an instantaneous slope. So if we didn't know exactly what the function was to take the derivative, we could just approximate that slope as like a little change in reactivity over a little change in that x coordinate. So yeah, it would absolutely just be the change in reactivity divided by the change in x. And if we're talking about change in a quantity, what does that symbol delta tell us about? What is that telling us to do with that quantity? Final minus initial, right? So it would mean like take the final reactivity of my system minus the initial reactivity of my system over the final value of whatever x is minus the initial value of whatever x is. So that's the fundamental definition of any reactivity coefficient, and that's how we can simplify it as a finite difference if we don't know what the derivative is or we don't know what the reactivity function is. Um, and so the units of this are going to be based on the units of reactivity divided by the units of whatever the quantity is. So like if the quantity is temperature, this might be like degrees Fahrenheit or degrees Kelvin. If it's a pressure, then it might be like PSI or kPa or something like that. Um, so that's in general what our reactivity coefficients are. We had defined the temperature coefficient last time. And so and we had kind of talked about how some different ways that temperature can cause feedback effects. The main one in terms of our cross sections is that Doppler broadening phenomena, and then also changing density. If we heat something up, the density changes. The number density is based on the mass density, and also the cross sections, the macroscopic cross sections depend on the microscopic cross section. So your big sigma is your little sigma times the number density, and the number density is the atom is Avogadro's number times the mass density divided by the atomic number. So if you change the mass density of your material by like heating it up or cooling it down, you change the number density of your material, and that means that you change the macroscopic cross sections of your material too. So the cross sections get changed both because of density changes as well as because of the fact that the when we talk about Doppler broadening, that's affecting the micro cross section. That's affecting little sigma. And both of those things affect the macro cross section. The macro cross section affects all of our reaction rates. So there's heavy temperature dependence in our system because of these phenomena. And so we use the temperature coefficient of reactivity to talk about the rate of reactivity change in our system due to some change in temperature. So if we're talking about a temperature coefficient, then we replace that variable x with capital T, and that capital T is representing a temperature, could be in Kelvin or Fahrenheit or Celsius. And ultimately, with any reactivity coefficient, the main thing that we care about is the sign of that coefficient. Is it positive or negative or zero? Because that's going to fundamentally tell us what kind of feedback that property is going to have on our system. And so we had an illustration of that last time, where so we wrote the definition of reactivity in terms of K effective. We then use the definition of reactivity, that it's that if the temperature coefficient of reactivity is the derivative of my reactivity with respect to temperature, then we took the derivative with respect to temperature and we plugged in that reactivity definition to basically rewrite my temperature coefficient in terms of K effective and the change in K effective with respect to the change in temperature. Um, and so that helped us see that K effective squared is always positive. So the sign of whatever alpha t is going to be the same as the derivative of K with respect to temperature. So if if the temperature coefficient is positive, that means that the temperature derivative has to be positive, and that means that if I increase my temperature, I also would end up increasing K effective. Whereas if my temperature coefficient was negative, that means that the derivative is negative. So if I were to increase temperature, the result on K effective is that K effective is going to go down. So this, when the alpha T is negative, temperature goes up, resulting in K effective going down. a negative temperature coefficient exhibits negative feedback, right? That temperature went up, resulting in my reactivity going down. So when we talk about like positive and negative feedback, it's like if my reactivity coefficient is positive, I'm going to have positive feedback, and any increase in temperature is going to result in an increase in K effective. Whereas if my temperature coefficient is negative, then any increase in temperature is going to result in a decrease in K effective, which is ultimately what we want. So if you make a startup company and you try to build a reactor, and then you go to the NRC and you show them all your results, and you have a bunch of positive alpha T coefficients, they're probably not going to license your design because it would be very unsafe to have reactors that had positive alpha coefficients. Um, so that's kind of just, and this is mostly review from last time, and we kind of stopped right around here. I think this is technically the slide that we stopped on, where we were just remarking that there's other reactivity coefficients too. They all have the same fundamental functional form. So like if you were going to remember anything, I would just remember the general form, and then based on what my quantity is, I could rewrite it however I wanted. And also this equation right here, this equation would look the same for any quantity that you took derivatives with respect to. So notice that if I have an alpha p coefficient, then my formula looks the exact same. It's just that I'm taking a derivative of k with respect to p. Or if I have an alpha v, a void coefficient, then I'm taking the derivative of k of effective with respect to that void fraction. Um, so when we talk about the pressure coefficient of reactivity, it's more important in gas reactors because the pressure is more has more of an effect on the gas, whereas in our reactors, they're mostly pressurized water reactors. That means that it's water is the coolant and it is operating at a very high pressure. The pressure is so high that any like even if it's a pretty decent like a significant change in the pressure of the system, it's not going to affect the reactivity that much because the pressure is already at like such a high point. You can change, I think the number, if I'm remembering it right, is that the reactivity feedback of like a 2 bar pressure change is equivalent to the reactivity feedback of like a fraction of a Kelvin temperature change. So that the pressure can vary a whole lot before it starts to affect the reactivity of our system compared to things like temperature. The void fraction is more important in boiling water reactors because in a boiling water reactor, you have your core and you have coolant that goes like comes in through the bottom of the core, passes over these fuel elements, but as the coolant passes over them, the reactor itself is not pressurized as much as a PWR is, which allows the coolant to actually begin to boil while it's in the core. So like as if you think about the quality, like how much steam you have, it's zero at the bottom because it's all water coming into the bottom of your core. And as you go vertically upward, you have a change in quality as a function of your vertical change in height. And if you have steam forming in your core, that changes the like cross-section properties of your moderator. Like if you were comparing one of the void locations where there used to be a bunch of water, but now there's like a little steam bubble. How would the amount of moderation compare in the void compared to in the water? There's going to be less, right? There's going to be way less moderation because you can think of steam as just like it's water, but it's just very, very low density. It's like you have very few atoms of water per unit volume kind of bouncing around as a gas versus kind of being collected tightly together in a liquid. So you have effectively water with a very low, low density, which means you have a very low amount of moderation in those voids. Um, if the neutron is passing through like a steam bubble compared to passing through water, how's the leakage going to compare in the steam bubble versus the leakage? There's going to be way more leakage if we're moving through steam versus through water. And then how is the absorption going to be affected if we have less moderation? There's going to be less absorption. Perfect. So as a result of that, so that's going to affect like what's happening with our neutrons in terms of how likely are they to become moderated. And if neutrons don't become moderated and they don't reach thermal energies, then it's less likely that they get absorbed into fuel and cause a new fission. So we care a lot about the void coefficient in like boiling water reactors for that reason. You can also define like a density coefficient, and I think those are like the main coefficients that you'll see: temperature, density, void fraction, pressure. You might see other ones, but they're not going to be as common. Um, so in terms of these effects, one of the things that we want to be aware of is that when you have some transient occur in our reactor, there's some responses that are going to be like very, very fast responses that happen almost instantly when the temperature changes. And there's going to be other effects that happen over slower, longer periods of time. So we want to be aware, whenever I was talking about in the earlier slide, different changes to the reactor state, we want to be aware of these changes. Another thing that's probably good to be aware of is the rate at which these changes affect my system. Are they very fast effects, or do they take longer to change my system's reactivity? And that's kind of what we're talking about here. So in all of the reactors that are producing power in the United States and most of the world, it's solid fuel like uranium dioxide pellets. So if if we have some reactivity change that results in our like power increasing, what's going to be the first thing in our reactor that changes temperature? The coolant is getting heated up because of the fuel, right? So it's the fuel. The fuel is what heats up first. Um, and so because of that, if the fuel is the first thing to heat up, it's the first thing to respond to any temperature changes. And so usually the temperature coefficient is the one that we care most about because it's going to be the thing that responds fastest. Um, Once you have the fuel producing more fuel heating up, it's going to be transferring more heat to the moderator, but the effect of the moderator temperature going up is a bit of a slower effect. So as a result of that, it's common to say we've got this temperature coefficient, but it depends on some things that take a long time, and it depends on some things that take not as much time. So we can break the temperature coefficient up into a prompt part and a like a delayed part, which doesn't relate to prompt and delayed neutrons, but just is it a fast effect or is it a slow effect? So and it's so we'll have an alpha T for the fuel. And this could depend on time, and it could depend on temperature. And we'll have an alpha T for the moderator. And that could also depend on time and temperature. And so we're saying that the fuel is the prompt effect. The prompt effect is based on the temperature of the fuel, and then the delayed effect is based on the moderator. Um, So in general, we can talk about an alpha T coefficient for the whole reactor, which is kind of like what this quantity is. And then we can break that up and we can say, I have a part of this coefficient that's coming from the fuel, and I have a part of this coefficient that's coming from the moderator. And so we want to kind of be aware of what are the phenomena that's going to influence the temperature coefficient for my fuel and what's going to influence the temperature coefficient for my moderator. And so this is kind of going back to something we talked about very early in, but we can revisit it and hopefully it will make some more sense now. Um, when we're talking about the temperature coefficient for the fuel, that's mostly due to how the fuel responds due to changes in my cross sections. As a result of changing temperature, I'll change cross sections, which is the main thing that's going to affect my reactivity. And this is mostly due to Doppler broadening. So if you remember like way back when we started showing plots of cross sections of nuclei, um, we noticed that, for example, I believe this is uranium-235. It's some kind of fissionable nuclei where at high energies, the cross section is relatively low, and then as you decrease the neutron energy, you increase these cross sections. And as your energy decreases, you go through this intermediate range or like the slowing down range where your fuel has all these crazy resonances in its cross sections. So if we were to like say look at one of these random resonances and we were to look at it kind of zoomed in, what we would see is that that resonance will actually change if you change the temperature of your system. So T1 here, T1 is lower than T2, which is lower than T3. So T1 is like the cold temperature, and T3 is like the hot temperature. And so notice that when my temperature is cold for T1, my resonance is like very kind of is kind of skinny and tall. So if the resonance is skinny and tall, then it's only going to be like a small range of neutrons that get absorbed within this resonance because it's like a thin range of energies that can be here. But if my temperature is high, then these resonances broaden, and now there's a much bigger range of energies where a neutron could get caught in that resonance and then be parasitically absorbed, which would result in it not causing a new fission. So if neutrons are getting absorbed here, they're probably getting parasitically absorbed and not causing a new fission. Whereas if they're getting absorbed here, then they're probably going to cause a fission. So if the temperature of the fuel increases, these resonances broaden, that increases my absorption, which is ultimately, if my absorption is increasing such that my neutrons are being absorbed and not causing new fissions, what's going to happen to my reactivity if I increase the temperature of my fuel? Is the reactivity going to go up or is it going to go down? It's going to go down, right? If the absorption goes up such that we're not getting new fissions, we're just absorbing the neutron and it's like just getting absorbed in the fuel and not fissioning, then that result means that this temperature coefficient is negative. And that's what we want to happen. It's a good thing that our fuel does this because it basically means that our fuel kind of has its own built-in negative feedback mechanism that if we start to increase our temperature, these resonances broaden, that results in neutrons being like parasitically captured, and that results in ultimately a negative feedback effect. So that's kind of a review and revision of these the Doppler broadening phenomena and kind of connecting it to how it affects reactivity, specifically the fuel reactivity coefficient. Um, when we talk about the moderator coefficient, that can be due to lots of different things. It's kind of like a combined effect of how does temperature and also water is like it's a funny like when you take thermodynamics, you realize that like if you change temperature, you end up changing all of these other variables. So like it's one of those things where it's kind of changing temperature ends up changing all of these other things, which all end up having various effects on our system on the behavior of that moderator. Um, but so ultimately, we can talk about a couple key phenomena. Um, we're imagining a light water reactor, so like a power reactor that has water as the coolant. We're imagining that we're going to increase the temperature of the coolant in our reactor. And then we want to think about how that's going to affect various properties of our system. And the first thing we want to think about is how it affects the neutron energy spectrum. If we end up increasing the temperature of the moderator, how does that affect the neutron energy spectrum? It's going to shift it to the right. And in what part of the spectrum does it shift? The thermal part, right? So it's going to, we'll say shifts right in the thermal region, right? We're trying to envision that plot that kind of looks like this, where you have your Maxwellian in the low energy, you have that 1 over E in the slowing down region, and then you have that fission spectrum in the high energy. So it's like if this is thermal and this is intermediate and this is fast, we're talking about what's happening in the thermal region. This was the Maxwellian distribution was what the thermal part of our spectrum looked like. And so what we're saying is that the only thing that we're shifting to the right is the Maxwellian, that thermal part of the spectrum. So if that thermal part of my spectrum is getting shifted to the right, what it means is that maybe I now have something like that, where it's not really affecting that change doesn't affect any other part of the spectrum. It only affects the thermal part. So that peak of my thermal spectrum is going to like get shifted to the right. So some of those neutrons that would have been like in that thermal part, thermal range, are now finding themselves in that intermediate range where it's more likely that they could be captured and not cause a fission. So ultimately, when you shift that spectrum to the right, you get more absorptions that don't cause fissions. In other words, you're increasing the capture to fission ratio, and that makes the moderator temperature coefficient partly negative. So that is a resulting negative. Oh, let me use a color that everybody can see. More negative. Hopefully that makes sense. If the Doppler broadening makes sense, this is connected to that. You're shifting that spectrum into the Doppler range, so you get more Doppler broadening as a result of that spectrum shifting to the right. Um, so that's that first part. This is about how we are affecting like the cross sections, like our cross sections and our sigmas and things like that. The other thing that a temperature change can affect is more of just like the kind of physical properties of our coolant. Like so if we heat a coolant up, like if we heat up water, what's gonna happen to its density? Is the density gonna go up or down? The density goes down, so the density will decrease. And the reason that that happens is because the coolant will also expand. Like ultimately, that's what's happening is that you have some amount of mass that is heating up and is expanding. So its volume is increasing, but its mass is staying the same. So as a result, the density decreases. You get like voids forming in your coolant. We already talked about how the voids forming will result in less moderation. It will result in less thermal fissions, and it will result in ultimately more resonance absorption. Um, and all of those effects ultimately have the same like consequence on our system that both the neutron spectrum effects and these coolant density effects ultimately result in negative feedback. So that means that both of these effects are happening in the same direction. So that means that the void coefficient for a water moderated core is going to be large and negative. Both of these are like negative effects that are adding together. So the combined result is that we have a very large negative coefficient of reactivity for the moderate. Um, and so when we're talking about a liquid moderated core, it's the thermal expansion that gives us the dominant reactivity effect, whereas in fuel, it's the cross-section changes that gives us the dominant reactivity effect. So I wanted to talk real quick about so this is that energy spectrum that this is the plot that I was kind of crudely sketching up top here, right? And I wanted to try to convince us, if we weren't already convinced, why it's only the thermal part of my spectrum that changes. So we had just said that it's only the thermal range that is impacted by a temperature change. So we want to understand why that is. Ultimately, we know that the peak of this, so if this is a Maxwellian distribution, the peak here, like the E value or the T value that corresponds to this peak is like the T average of the moderator. That's what that ultimately, it's the temperature that corresponds to E equals KT for our moderator. So really it's the energy that corresponds to this, or yeah, it's the temperature that corresponds to that energy. And so if we were to heat something up, the average temperature is going to increase, which is going to take my T average, it's going to shift it to the right, which is why the peak shifts to the right. And if I decrease the temperature, that peak is going to shift to the left, which is the average will shift to the left, which will shift the peak to the left. So increase or decrease results in the spectrum either shifting right or left. And so we might be wondering, like, why does this only affect the thermal spectrum? And partly I'm bringing this up because this was also something that was missed on exam one. Um, it's only the thermal spectrum, and hopefully I can convince you why on the next slide. Part of what to recognize is that on this X, on the E axis, what kind of scale is this? It's a log scale, right? So that means that things are varying considerably going along the axis. And so if we think about the fact that it's on a log scale, and we think about the fact that it's the E equals KT calculation that's giving us those energies like in the thermal range, we could think about what's like the maximum possible temperature our fuel could ever be, or in other words, what's the temperature of our fuel where once we get there, we have like very, very bad problems. The melting point, right? If our fuel ever gets to its melting point, T melt, we are all in big trouble. So we can probably pretty reasonably say T melt is like the highest temperature our reactor could ever be. Therefore, if I do a calculation of K times T melt, that's going to correspond to like the fastest neutrons could be moving just as a result of the fact that they're in thermal equilibrium with their environment. So for T melt, the T melt for UO2 is about 2,800 degrees Celsius. This Boltzmann constant is in units of EV per Kelvin. So if I like take that 2,800, convert it into Kelvin, and then do K times T, if I do K times T melt, then what I'm going to get is approximately 0.26 EV. So that tells us that if our neutrons are in thermal equilibrium with a reactor that's like melting down, the peak of that Maxwellian would be at 0.26 eV. Um, if we're talking about neutrons that have any energy like less than 1 eV in our reactor, they're not that energetic because of thermal effects. They're that energetic because they were born really, really fast from fission, and then they're on their way to slowing down to those low thermal energies. So if you think about like going back to this log scale, 0.26 EV would be like maybe somewhere around here, right? This is e to the 0, so that would mean 1 EV is right here. So 0.26 is going to be somewhere a little bit to the left of there. So at most, this Maxwellian would maybe shift to like right here, but it's not going to shift like any further than the peak wouldn't shift any further than maybe 1. So if I ever ask you, like, how does a temperature change affect the fast spectrum of our reactor? Or how does a temperature change affect the slowing down spectrum? It doesn't have any effect. The temperature change would only affect the thermal spectrum of the thermal part of our energy spectrum. When we are talking about those moderator effects, that was for a liquid moderated reactor. There are some reactors, like high temperature gas reactors, like if y'all are familiar with X Energy, their design is a high temperature gas reactor. They use a solid moderator. When reactors use a solid moderator, do y'all know what material they commonly use? Graphite, yeah, perfect. So that's commonly going to be graphite. If we have a solid moderator, it's going to be just like a big old chunk of carbon, basically, high quality, high density carbon. Um, and so if our moderator is in a solid like graphite form, then if it has a temperature change, it doesn't have as much thermal expansion as like water does when it's heated up. Um, so if they don't experience thermal expansion effects, the main effect from a moderator that's solid is just going to be that shift in the thermal energy spectrum, which is going to affect our cross sections. So it's like when we talk about a solid moderator, the solid moderator is only affected by this first information right here. This second part of the information that's talking about expansion and contraction, those effects aren't as pronounced if it's a solid core. Solid moderate in the core. Um, and so, something I wanted to mention, we've talked about the energy spectrum shifting to the right based on an average increase in the kinetic energy of the particles in our medium, or shifting to the left as a result of like a decrease in temperature and the decrease in that average energy. Sometimes if you read papers or if you even read Dr. Svedkov's notes, they'll use the term hardening. they'll say something like this sentence right here: an increase in the moderator temperature results in a hardening of the neutron spectrum. That means just shifts it to the right. Hardening just means shifting to the right. So if you are ever seeing that and confused by what that means, we actually understand it's just they're using funny terms to talk about. So that's solid moderators. And then ultimately, when we talk about feedback responses, if we think about alpha t being positive or negative or zero, we've already talked about different feedback effects. And so basically what we want to say is that so like imagining we had before, we've talked about how various changes to our system, like if we increase the reactivity, what's the population going to do as a function of time? We can talk about how that is influenced by a reactor that also has feedback. So before we talk about the feedback, if we had like a critical reactor and we inserted positive reactivity by like removing a control rod, um, what's the immediate response to the system power going to be if we have like an increase in reactivity to the system? It's going to have like a prompt jump, right? There's going to be a prompt jump in power as a result of the increase in reactivity, prompt jump in power. And as a result of the increase in power, what's going to happen to the temperature of the fuel? It's going to go up too, right? The temperature of the fuel is going to increase. So power goes up, temperature goes up. As a result of that, there's feedback effects where the temperature can act back on the rest of the system that can ultimately change the system, which can impact, which is going to be impacted by the sign of my alpha T temperature coefficient. So if alpha T is positive, that's positive feedback, and we get like a runaway effect where increasing power increases temperature, increases the reactivity, increasing power, increasing temperature, increasing reactivity, and that will continue on without limit if you have positive reactivity, which is bad. If you have negative reactivity, then the temperature increase results in a decrease in reactivity, which will ultimately allow for our system to become stable again. The effect of that feedback is going to act back on our system. It's almost like we increase reactivity, but then temperature is slowly adding negative reactivity into our system until the reactivity of our system gets back to some reactivity of zero, steady state kind of situation. And then you can have a very negative reactivity coefficient. So this is alpha t being negative. This is alpha t being like really negative. And the more negative the reactivity coefficient can cause a power overshoot, where you get some increase in power and some response that results in the power like not increasing exponentially, but kind of leveling off. But then the decrease in reactivity is so much that our power will actually like drop down if the alpha t is too negative. So generally, there's kind of like a sweet spot for alpha t where it helps our system become stable, but it doesn't result in our system like having like oscillatory effects. And so those are all illustrated on this slide right here. This was alpha t being positive. This was alpha t being negative or zero. And this was alpha t being like very, very negative. And so that was the power overshoot where it's like the negative coefficient causes our system to stabilize, but then the temperature has increased has resulted in such like a negative insertion of reactivity that the temperature like drops down and the resulting power drops down. Um, so those are some possible temperature feedback responses that you could have depending on if your alpha T coefficient was positive or negative or very negative. So this is just a table that shows different kinds of reactors and their various values of alpha T. Excuse me. Here, alpha T is given in a percentage per degree Fahrenheit. Um, so yeah, different reactors have different negative reactivity coefficients, but notice they're all negative. Um, So when we talk about operating reactors with feedback, that kind of complicates how we have to deal with systems. Part of the thing that's kind of funny is that, like, if you imagine our reactor is cold, like we have just put the fuel in, we've just put the water in, but like the reactor isn't isn't like producing a lot of power yet. Maybe it's like critical, but it's at a very, very low power so that it's like basically at like room temperature with the rest of the reactor materials. If we want to increase the power of our reactor, we're going to end up having to increase the temperature of our reactor, but our reactor is going to have negative feedback, which means that we kind of have to think a little carefully about how do we increase power without having the feedback effects ultimately take my power back down. So when you're like starting up a reactor, there's a balancing act between removing reactivity and also increasing temperatures such that you basically get to your reactor slowly ramped up to some higher temperature critical operating state. So basically part of this is that reactors actually will have heaters within them that can heat the coolant up before it goes into the core. You also have control rods that can be inserted like at the beginning of when the reactor is cold, the control rods are going to be like almost fully inserted in the core. And to bring the reactor up to critical, you're going to slowly raise these control rods out to basically compensate for the fact that as my temperature goes up, it's adding negative reactivity to the system. So I can compensate for that by like slowly pulling my control rods out, which adds some extra positive reactivity to kind of make up for what the temperature effect is causing. Um, so if you think about like where your control rods are when you start the reactor at cold to when the reactor is like operating at full power, there's going to be a difference in the height. And those control rod positions are referred to as there's like a hot critical state and then there's a cold critical state, which is where the control rods are when the reactor is cold and when the reactor is hot and operating at full power. Um, Something that we might want to do in a situation just kind of like what we described is calculate what the reactivity coefficient is, or at least like maybe approximate what the reactivity coefficient is. So if we think about that system where state one is the cold reactor at startup, and state two is the reactor when it's like near full power, then at those states, we can define the multiplication factor and the temperature. So like we're basically going to have a K effective 1 and a K effective 2, which is my multiplication factor at states 1 and 2. And then we are going to have a temperature 1 and a temperature 2, which corresponds to like my temperatures at states 1 and 2. So if I have K effective, how could I write my reactivity in terms of the K effectives? How would I write reactivity as a function of K effective? Perfect. Yeah, K minus 1 over K. So in this case, reactivity 1 would be the K effective 1 minus 1 over K effective 1. And then similarly, the reactivity 2 would be the K effective 2 minus 1 over K effective 2. So if we know our reactivity 1 and our reactivity 2, we also know the temperature change, which is just T2 minus T1, then we can approximate alpha T as the change in reactivity over the change in temperature. And ultimately, what that's going to give us, if we plug in these definitions, is that I get 1 over delta T times the fraction that is K effective 2 minus K effective 1 over the product of those K effectives multiplied together. K effective 2 times K effective 1. So going from here to there, you're just plugging in the reactivity definitions. This becomes row 2 minus row 1. You plug in the definitions for row 2 and row 1. You kind of group terms and you simplify like over a common denominator. And ultimately, that's how you can get that expression right there. So if our reactor was going through the startup procedure and we had like an in-core detector where we could determine what K effective is, and if we had some kind of temperature sensor that can tell us the delta T, then this is a way that we could approximate what the alpha T of our reactor is, um, based on knowing the final and initial temperatures and knowing the final and initial K effectives. Question.
Is that one bottle?
Yeah, those are being, yeah. Mhm. Yeah, those are being multiplied. So, I guess going from there, that's the last stuff that I wanted to say about the reactivity coefficients. Um, and in terms of chapter 7 stuff, there's just a couple other things that I wanted to talk about, which is mostly about a phenomena called perturbations, and another thing, which is similar to what you've already seen, basically like input and uncertainty analysis. So, um, in when we're talking about these point kinetics equations and we're talking about like a reactivity insertion to our system, you can think of that reactivity insertion as like a perturbation to the system. And so there's a whole field of math called perturbation theory, which is ultimately a way that you can estimate how, if you have like a system and you have some input to that system, how does the system respond to that input? Um, and so with perturbation theory, you can do what we were is another way to calculate what those temperature coefficients would be without having to do like a bunch of individual calculations like we just saw, where you had to like know what's happening at state 1 and know what's happening at state 2. And like ultimately to get an alpha T, you would have to do that a bunch of times. Like you wouldn't look at the temperature change over the whole going from cold to hot. You would do like a very small temperature change and you would look at the corresponding change at K effective. And you would look at another small temperature change and look at that corresponding change in K effective. So you would actually have to do a bunch of small calculations from state 1 to state 2, to do what we had just said. Whereas with perturbation theory, you can kind of get a just nice equation that'll tell you everything in one shot. Um, with perturbation theory, for this like mathematical theory to be valid, we have to assume that the reactor is like initially near critical and that any changes to our system are small and can be treated as a small perturbation. Um, in perturbation theory, they'll use, it's kind of similar language to what we're familiar with, except their initial system before you made any change is called the unperturbed system. And then you do something to the system, like you insert reactivity, and then that insertion causes some perturbation to the system. And they use like a delta for the symbol of the perturbation. So like if we're inserting some if we're increasing the effective multiplication factor, there might be some positive perturbation delta K effective to the unperturbed system. As a result of that perturbation or that change, there's a new system which is called the perturbed system, and they'll use a subscript U for the unperturbed values and a subscript P for the perturbed values. So we can basically write our equations in like matrix form, and we can use the symbol U to talk about this would be like my matrix system for the unperturbed reactor before I do something to it. We're going to have some perturbation to our reactor, like some change in K effective, some perturbation in the K effective, which is going to cause perturbations in all these other quantities. It might affect the affecting K effective, which is going to affect my flux. And as a result of my system changing, it's going to have a perturbed state and an unperturbed state. And so the loss operators and these gain operators can be expressed also like in a perturbation form, where we're saying the perturbed loss operator is my initial loss operator plus whatever change to the loss operator I have because of the perturbation. This is saying a similar thing with the gain operator. So we can write the unperturbed system like this. We can write the perturbed system like this with subscripts P. And then we could basically go through a process where we write the one group diffusion equation and we assume these kinds of perturbations in things like the absorption cross section and the value of nu F sigma F. And if we go through that process, which I'm going to skip the derivation, and the derivation is also, it's not part of the homework, so it's not like a derivation for the exam, but ultimately that derivation gets you to this point where this is an equation that gives us the perturbation in K effective based on only knowing unperturbed values of my system. So phi u, for example, represents my unperturbed scalar flux, and then the delta terms are just perturbations in various properties of my system. Like I might have a perturbation in my nu f sigma f, a perturbation in my diffusion coefficient, a perturbation in the absorption constant. But ultimately, if we can quantify what those perturbations are, we would also probably know what the unperturbed flux is, because if the reactor was critical before, then we could use expressions that we're familiar with for like the fundamental mode flux shape for those reactors, like in the unperturbed state. Um, and yeah, so if you knew what those perturbations were and you knew what your unperturbed state was, this is how you could compute what the change, what the perturbation or the change in your K effective is, resulting from those changes in my properties, and you could do it all in one shot without having to do a bunch of static individual calculations. So that's as far as we're gonna go in terms of perturbation theory. That's one of those topics where like you could take a whole math class just on perturbation theory. So I think that's all that I wanted to say about that. And I kind of wanted to start connecting that into uncertainty. There's some similarities, both mathematically and also conceptually, between perturbations and uncertainty. The fact that we have perturbations can be like kind of a form of uncertainty, especially if you're not aware about what those perturbations might be or how those perturbations might affect your system. It's also a good thing to just know that like when we're dealing with quantities like all of the quantities that we talk about in nuclear engineering, like cross sections, these are measured like experimental quantities. Those things have uncertainties associated with them. And so knowing about uncertainties in our measurements is going to affect the things that we're calculating. Like if we're calculating K effective based on material properties, but we have uncertainties in those material properties, that's going to mean that we have an uncertainty in our K effective too. So if we have some variable, if we have some function f that's a function of multiple variables, x1, x2, all the way up to xn, then if those variables x1, x2, all the way up to xn have their own uncertainties or their own errors, like a delta x1, delta x2, all the way up to a delta xn, then we can propagate the uncertainty of all of those inputs to determine how that affects the uncertainty in the output of my function. And that's with the general error propagation formula, which says that the error in my function squared is going to be the sum of the following products. I'm going to take the partial derivative of my function with respect to the first, whoops, with respect to the, that's supposed to be a 1, not an I, with respect to the first variable times the uncertainty or the error in that first variable squared. Shit, and that's supposed to be in 1, 2. And then I'm going to have the uncertainty in my function, sorry, the derivative of my function with respect to the second variable times the uncertainty in my second variable squared plus. And I'm just going to have a bunch of these terms for however many input variables have uncertainty. So I could have up to n terms. This would be df dxn times the uncertainty in xn, and that whole thing is squared. So hopefully that's familiar from like Mariano's class when you did error propagation and uncertainty propagation. These are the exact same calculations, and we're fundamentally talking about the same thing. Um, so like an example of that is like a simple formula like K infinity. When we're calculating or approximating K infinity, we're doing nu F times sigma F over sigma A. Each of those is like nuclear physics quantities that comes from Janus. In Janus, these all are tabulated from like various experiments. So there could be uncertainties in nu F, uncertainties in sigma F, uncertainties in sigma A, which would mean that if we're calculating K infinity, there could be an uncertainty in that value too. And if we're designing a reactor to be critical, but we're not aware of those uncertainties, we could end up making a dud if we weren't aware about the fact that we might not fully have confidence in the material property numbers that we are using. So in the homework, you have a problem that's more about this kind of uncertainty calculation, where you are finding the error in the critical mass of a reactor based on the fact that there's an error in the K effective. So ultimately, if there's an error in the critical mass, we're assuming that the error in K effective is only due to an error in the mass. So ultimately, what we're given is that there is some uncertainty in our reactivity, which has this corresponding uncertainty in K effective. And those uncertainties are related by just basically just by doing a derivative. So if you have the definition of reactivity and you take the derivative, that's how you can get this expression. Um, so if I know the uncertainty in my reactivity, I could also compute what the uncertainty in my K effective is. And I want to know, based on that uncertainty in K effective, what's the error or the uncertainty in my critical mass? So I'm going to need some expression for my critical mass that as a function of K effective. And the way that I'm going to do that is that it's a bare spherical reactor. So I can use some of my definitions from like one group diffusion. So I could write K effective for a spherical reactor. Also, if it's a spherical reactor, BG squared is a known quantity. And do y'all remember what's BG squared for a spherical reactor? Yeah. Yeah, and then the whole thing squared, right? So it's pi over the extrapolated radius of our reactor, whole quantity squared. So we know BG squared, we know a formula for K effective. So ultimately what we could do is we can take that definition, plug in that value for BG squared, and then we could take this expression in step one and we could get R by itself. In other words, what we're going to do is we're going to get R as just a function of K effective and constants. There's going to be other things in there, but the only thing that has a functional dependence is K effective because everything else is going to be constant. In other words, none of the other things have uncertainties associated with them. K effective is the only variable with uncertainty, only variable that has a delta on it. So if I have this relationship between my radius and K effective, I can relate the radius to the mass. In other words, I can relate the mass of the sphere to the dimensions of the sphere through what quantity? What quantity can relate the mass of an object and its dimensions? If you wanted to get the mass of a sphere and you knew the radius of the sphere, what would you do? Density, right? Density is the thing that's going to relate the mass and the dimensions. So you would say that the density of my object is its mass divided by its volume, where this rho sub m, that's a density equation. So you've got the volume. You can get the volume because you know it's a sphere, so it would be like 4/3 pi r cubed. And then the density is going to be you treat the density as another constant. And so this is going to give us the mass. Ultimately, if I plug in the density formula or the volume formula in here and move everything to one side, I'm going to have the mass of my sphere as a function of K effective. And from there, I can do error propagation on that mass function. So ultimately what I want to get is mass, which is just a function of K effective and constants. And if I get the mass that only depends on K effective and then everything else is a constant, then the uncertainty in my mass is just going to be the derivative of my mass with respect to K effective times the uncertainty in K effective whole quantity squared. So you'll get an expression for M. You could take the derivative of that to get dm dk. And then the uncertainty in K is another quantity that's given. And then from here, you can basically get an expression for what that mass uncertainty is. So your final answer is just going to look like this simplified, where you just say the uncertainty in mass is, and you have some expression that's going to depend on constants, K effective, and the uncertainty in K effective. Um, so those are the rough steps. That's a little bit of just like a kind of homework help before, since we're not going to have the help session before the exam. I think that this would be like the main problem on the homework that might be a little tricky. So I wanted to make sure that we talked about the steps so that you had a decent kind of roadmap for how to approach this one. As always, if you end up with questions about this or about anything else, let me know sooner rather than later. We're kind of at the point where, so this is like the last thing that I wanted to talk about. This would be like anything after this is going to end homework 6, and that's going to kind of close the scope of exam 2. Um, so we're not going to have a homework help session because well, how to say, we could still have the homework help session on Friday. It's just that we're going to have the exam on Thursday. So yeah, basically, if we have homework questions that we want to get addressed, getting those addressed sooner rather than later, and like we're going to have the rest of class time. So at this point, I think I just wanted to talk about the exams, pass back exams and quizzes, and then we could just use the remaining class time to answer any questions that we had before we go off on our way to prepare for the exam. So this is what the like distribution for the exam 1 scores looks like, and it kind of was changed. When I saw these, I thought that I wanted to go back and see if there was like a way that I could help things along and see if I could be a little bit more like lenient on some of the partial credit. So some of those scores ended up getting shifted to the right. I think I had more people in the 70 bracket after I kind of added some points. So the distributions look like that. Keep in mind, and I think I heard some people discussing the weights of like, if you go in the syllabus, you can see how everything is weighted in terms of assignments. Of all the exams, exam 1 has the lowest weight. So even if you didn't do hot on exam 1, that isn't gonna like mean that you have to, that doesn't mean that you're in a hole or anything. It means that you want to make sure that you're improving though, because if you have a bad score on exam 1 and on exam 2, then it becomes pretty tough to make up something like that. So part of this is like getting just familiar with the class. We've come a long way since we actually took exam 1. It's been like 3-4 weeks since we took exam 1. So we've already learned a lot since then. Hopefully we've been reflecting on like how to prepare for these exams, and having this exam back should hopefully help that for exam 2. So let me go ahead and start passing those back. And I guess I have quizzes as well. So I guess I'll do quizzes first. Daniel, Bert, Ebube, Jay, Joshua, McMahon, Axel, Shimobi, Anne, Connor McLean, Cassandra, Carson Corbel, Colby, Raul, Roman, John Belts, Jesus, Mariam, Mhm. Joshua Reed, Jake, Tyler, Vincent, Raya. So there's your quizzes. There were supposed to be three, and my quizzes are also mislabeled. So you got back 5, 6, and 7, but those are actually 4, 5, and 6. Apologies for the. It's just a typo on there. We've only had 6 quizzes. I will go ahead and pass the exams back next. Raul, John Dutz, Kyle, Cassandra, Marion, Jake, and Nicholas. Shinobi's not here. Jesus. We're getting our steps in today, sorry. Ebube, Roman, Colby, Vincent, Daniel, Joshua McMahon, Axel, Carson, Tyler, Bert, Elizabeth, Michael, oh, Jay, Joshua Reed, Samuel, Connor McLean, and Brad. So, take a look at those. Let me know if I like missed any, like if you answered something and I just like completely missed it, let me know about that for sure. Um, if you have any questions about the grading, I'm happy to, if you're wondering like, how come I lost points on this or what was the reasoning behind these points, feel free to let me know. Generally, if answers were incorrect, I tried to give partial credit for things that were like partly right about the answer. If things were so like depending on how much of the correct answer was there, I would give anywhere from like 10 to 50% on answers that were wrong. Some people lost points because like they had the right answer, but it was like a calculations problem where they didn't show work. So just keep in mind that like if you have a problem where it's telling you to like obtain some expression or perform some calculation, needing to show the steps is really important so that I know that you could get from point A to point B and that you didn't just like memorize an answer and put it on the page. So showing work was important. Knowing the right model was important because like some people like they saw a question and they thought that there were formulas that were like relevant, and so it kind of for some people looked like maybe we were like just writing down formulas that seemed like they were applicable, but then we were also mixing up models, and so like maybe on the multi-region problem we wrote the multi-group diffusion equation, which is bad because in the problem it said it's a one group problem. So like if we were using the wrong model for the wrong problem, um, I I I I graded according to the fact that like I was looking for stuff that was pretty specific. We also saw a lot of these similar styles of problems on the homework. So hopefully when we see those back and we reflect on the what we put down and what the answers were, like from the homeworks and things like that, if we're losing points, we're seeing where we lost points. We're using this as an opportunity to like reflect, and we are learning from our mistakes and moving forward. Um, like we said, the exam one has the lowest weight, partly because we're probably trying to get accommodated with the class, trying to understand what does the professor want, what does the professor emphasize. Now you've seen everything, you've gotten your exam back. So as you're preparing for exam one, hopefully having that back helps you prepare for that and helps us see kind of what to focus on. And yeah, so if there's any questions about those results, let me know sooner rather than later. And I guess at that point, that was the last thing that I really wanted to say that I had planned to say. So if y'all have questions, we can, there's like 25, 26 minutes left of class time. So if y'all had questions about, yes.
Alright, are you gonna post this?
I'm not going to post solutions. You guys saw most of these questions on the homework. So my response to if you want solutions would be look at the homeworks because the homeworks you get graded and you get feedback on those. So my advice would be to like go back to the homeworks, see which exams questions matched up with the homeworks and try to use the feedback that you got from the homeworks or just use the class notes to see what the kind of process is would be. And as always, if there's like specific questions about stuff, feel free to let me know. But like, I think that is partly what is helpful for us as students. Like, I'm not going to give you guys, there's no like makeup points, like, or exam corrections. But if you lost points, I would expect all of us to be going back and trying to figure out what points we lost, why we lost them, so that you're not going to see any of these exact questions on exam two, but the final is cumulative. So similar questions from there could show up on the final. A lot of the concepts do carry over, like we're still going to be like, and you guys are seeing that as we like all of the equations that we've talked about and derived in exam two came from equations that we started and developed in exam one. So like you might not be asked those exact questions, but a lot of the concepts and equations kind of carry through. So if we were making mistakes, getting those corrected. If you have questions about those things, definitely let me know. But yeah, um, thank you for the question. Yeah.
Uh, I don't semester, I'm assuming it's not gonna be an overall approach, right, with different.
Yeah, what I am partly kind of contemplating is making the reactor design problem be like an extra credit. So if I was gonna do anything to like curve or give like bonus points, that's probably how I would do it, which would mean that like on the syllabus, the homework and the reactor design problem were like a kind of grouped weight. Like they each had their individual parts, but then they were like grouped as a total. So I would just like take the reactor design problem out of there. So the homework weight would just be that combined range. And then I'm kind of still contemplating if I do that, how the bonus points would be awarded. But yeah, so I'm still trying to figure that out. I'll partly know that once I see exam two. Um, so yeah, I will keep you guys posted on that, and I'll let you know sooner rather than later. But I don't know exactly how I'm going to handle that. So hopefully that makes sense, and that hopefully that would be helpful to make that just be an optional kind of extra credit thing. I just don't know how I don't know what I would replace it with is the main thing I'm still trying to figure out. So yeah, if there was any other questions about the exams or homeworks or anything like that, feel free to let me know. Otherwise, if y'all don't have any questions for me, then y'all are good to go. Have a good rest of your day. Good luck preparing. If there's questions as you're preparing, please let me know. And if not, I will see y'all in class on Thursday, unless you have different testing arrangements. Yeah,
This question, right?
yeah,
To be honest, I didn't even know what I was writing.
okay.
So for like this, like over two, why was it thermal surprise?
Um, so the neutrons in a thermal reactor, you wrote that the neutrons have to be slowed down to thermal. What part of the reactor slows the neutrons down?
I was gonna say moderator. It was,
Yeah.
I was thinking between core and moderator.
Yeah, so in a thermal reactor, we need a moderator. Also because we need like we don't just need moderator, we need enough moderator for neutrons to like slow down sufficiently, which means that in a thermal reactor, the fuel is kind of more spaced out, and we need more moderator like in between fuel elements to allow for neutrons to be slowed down. Whereas in a fast reactor, we don't need a moderator, so the fuel rods can be closer packed together. So that means that like if both reactors have like the same power, then the thermal reactor is going to be like a larger volume. Yep, exactly. Yeah.
Thank you.
You're welcome. No, good. Wait, next week. So there will be a homework that's assigned next. Yeah,
Okay,
and that's going to be the last one. Yes, it's going to be assigned, but then it's going to be due in 2 weeks. No, that's a separate one. The reactor design problem is a separate thing, but is also set to be due on the last day of class. And that was the one that I was talking about that I might switch to make optional. I'm still just trying to figure out what the bonus points would go towards.
Okay, thank you.
You're welcome.
Question about. So if remember it's new.
Yeah, that's what I was.
Good. And if remember 3 and 4. Aren't they basically the same questions? You sort of describe the conceptual and detail. Isn't that just the same as the assumptions?
Yeah, I think in 4, I was partly looking for more of like the kind of the equations. I guess I thought, yeah, you're right, I could word it better. Because actually in part 3, I was looking more for like the concepts and the like what's kind of the background, and then number 4 was just kind of explaining. So basically number 4 is kind of like what I outlined in the slides, and I think number 3 is probably explained in the notes.
Well, I felt like it kind of switched the answers around. So
Yeah. Yeah, they're to answer your question, though, they're both kind of open-ended, so they are similar. But yeah. Mhm. Hey.
I'm gonna make a quiz 6
Oh.
last week.
Okay. Did you send me a note?
We talked about it last week. I don't know if I followed up or not. No, I did miss my, but I'm kind of everything kind of crazy getting pop back out with everything. So
Because for me to be able to get you to let you make it up, I need like I don't know, I need some kind of like documentation of it being like an excused absence.
yeah, we emailed like a
Oh,
about it.
okay,
So
okay. That was what I was trying to confirm. No worries. Let me just pull that up. real quick. Um, Remind me your name?
Josh, man.
Because yeah, if I got it, then we're all good. I just want to make sure. Oh, okay, yes, yeah, cool. How is do you have family in Kerrville?
No, I just I'm at the part of an org that